All right, let's talk about z-scores or a measure of relative standing. I want to find a way to measure a single data point relative to the data set that the data point came from. So here I have two sets, one called B, one called G. B gives me the heights measured in centimeters of not 5 men, but I think I have 10 points there. So 10 men, and then G also measures the heights in centimeters of 10 women. So number one wants us to plot the heights on the real number line. So let's get a visualization of what this data looks like. So for the men's heights, I have a point at 70, a point at 81, 65, 69, 66, 75, 64, 63, 77, and 71. All right, so those are all my men's heights. And for women, I have 54. Let's move this out of the way. 54, where's that? Right here. 65, 51, 52, 49, another one at 52, 55, 53, 56, and another one at 53. Okay, so that's what the women's data looks like. So number two wants us to discuss the significance of a man's height of 81. And so I want to think about the significance of that guy right there and a woman measuring a height of 65. I want to talk about the significance of these 2 points from their distribution. So the best way to do that is to look at z-scores. So let's look at the z-score of the height, 81 centimeters. So the definition of z-score, so let's remind ourselves of that. The z-score for data point x is x minus the average divided by the standard deviation. Right, I want to figure out how far away a point is from its center in terms of how many standard deviations that is, right? How far is that distance in terms of standard deviations? So the point of 81 minus the average, and the average of the men's heights is 70.1. The standard deviation of the men's heights is approximately 5.99. So everything here is measured in centimeters. All right. So if I did this, this is going to give me a z-score that's approximately equal to 81 minus the average of 70.1, and then divided by the standard deviation, right? How many standard deviations fit inside that gap? I get a z-score of about 1.82. Now, notice that this is a unitless quantity. It's no longer measured in centimeters because I'm taking centimeters and dividing it by centimeters. So it's a ratio. All right, let's do the same thing for the woman's height. Let's find the z-score of a woman measuring 65 inches, or sorry, 65 centimeters. So that is the height of 65 centimeters minus the center of her distribution, and the average of the women's heights is 54. The standard deviation of the women's heights is approximately 4.35. So if I find the the z-score of a woman having a height of 65, I want to find out how many standard deviations away 65 is from the center of 54. And if I do this, I get approximately 2.53. So what does this tell us? It tells us that this man right here that measures 81 centimeters is only 1.82 standard deviations away from his center, right? His center was 70.1. So somewhere right there. Right, so he's only 1.82 standard deviations away. The woman that measures 65 centimeters is more than 2 standard deviations away. She's 2.53 standard deviations away from her center, which was 54. Right, so even though that these distances are the same, right? If I take 81 and I subtract 70.1, right? That's about, what is that? That's about 11, I think maybe 10.9. If I take 65 and I subtract 54, that's also 11. So even though both individuals are 11 centimeters away from their center, men's heights have a wider distribution. They have a larger standard deviation. So this height right here isn't that surprising. It's only 1.82 standard deviations away. This woman measuring 65 centimeters, though, is surprising. It meets that significance threshold of being 2 standard deviations away from her center.